it's my honor to introduce our speaker, Professor Ankur Mehta. He is an assistant professor of electrical and computer engineering at UCLA. He received his PhD from UC Berkeley, and then he was a postdoc at MIT's Computer Science and Artificial Intelligence laboratories. And his research interests involve printable robotics, rapid design and fabrication, control systems, and multi-agent networks. He is also directing the laboratory for embedded machines and ubiquitous robots. So let's welcome him. Thank you.
Thanks, Mehta. It's good to be back here. As you mentioned, I did my PhD here, although in the many, many years I was around, I don't think I ever actually set foot in this room before. So, always something new going on here. Before I start, let me first say that, as a faculty, I don't do any work anymore. All the work that I'm going to be presenting here has been done by a research group and collaborations here actually at Berkeley with Kathy and Alex Pinion. You can see my team at our what's called our field station on Santa Monica Beach. We do a lot of work in our group on robotics, on controls, on many different things. We're always looking to grow, so just a quick shameless plug out there. If you're interested in going down to the sun and the surf, come find me after the talk. But so as Mehta mentioned, my interests sort of span a lot of different fields, a lot of different topics. But there's a common theme tying it all together that'll sort of give rise to the research that I'm going to be presenting here today. The idea is democratization. How do we take the engineering results, the research results that happen in all of our research labs and all of our education and schooling here in universities, and bring that out to the world? How do we, in particular, make use of automation technologies in computation to be able to do more to help the general public? And so this shows up in many different forms in our research. So one topic is the idea of being able to create engineered objects, robots, and responsive environments, and physical artifacts of the world, but not require so much infrastructure, don't require manufacturing tools and engineering expertise and background. This work has sort of been one of the cornerstones of my research lab on printable robots and design automation for robotics. I gave a talk on this at the EECS colloquium last year. It should be online if you're interested in more about that. Go ahead and check that one out. We're also working on control systems, on automation. How do we allow the control of these intelligent and engineered objects, again, minimizing the requirements on resources, on interdisciplinary engineering and integration efforts. We'll see some of that later on in this talk. But ultimately, it comes down to, overall, how do we improve the state of life? How do we improve people's experiences when interacting with machines, with engineered devices as we all are working towards as engineers here in the school? And of course, in order to bring this to more people, in order to bring this out into the world, I'd like to minimize the need for investment, for infrastructure, for building up requirements just so that people can make use of this technology. And that leads to the overarching vision behind the work that I'll be presenting today. This idea of improving people's lives as drivers by configuring the relationship between the drivers and cars. And the question we're trying to ask is, can we use automation, maybe autonomous vehicles or some kind of semi-automation, to improve the lives of the humans that are affected by this, the people who are sitting in their cars trying to commute to work every day? Perhaps a bit more specific way of putting this is to say that can we get benefits for traffic and transportation with the technology that we have, with the amount of automation that we have in our world today, with the amount of infrastructure in the built environment that we have today? How do we make the most use of that in order to see the benefits that we hope to see going forward with even more technology? And so I'll start with a bit of background. I was told that there's a lot of new students in here, so I'll work my way through some of the underlying backgrounds behind what we've been doing here. And I certainly don't need to convince anybody that traffic is terrible. And just saying that is good enough. We want to make traffic better, but there's actually a lot of studies behind this showing just how bad traffic is And so you can see there's an inordinate amount of time that drivers in America, and in fact across the world, spend sitting in their cars. Whether this is commuting to work or going to some other destinations, commutes are obviously one of the biggest factors of individuals sitting in cars. This gives rise to traffic and congestion, and it turns out there's a significant amount of waste associated with that traffic alone, sitting in on the transportation network, not going anywhere. And we see that gives rise to energy consumption, energy wastage. A significant portion of the energy in the U.S. goes towards transportation, and a lot of that is on highway driving. That sort of gives some motivation to the fact that we can consider optimizing highway driving first, move that out to the rest of the transportation networks, and we'll still be making a win. And this time and this energy that's spent translates to money, real money that's lost just due to traffic alone. All right, so that's that. It gets worse. There's a Senate bill that mandates the increased density of urban environments. People are going to be putting more and more businesses in the same amount of space. Where are the workers going to come from? Where are the customers going to come from? There's going to be more traffic density as we go forward over the next 25 years. And so there's predictions. People have studied this and said, things are going to get worse. Delays are going to get worse. Energy consumption is going to get worse. Not just through transportation, but specifically through traffic, through congestion. Okay, so what do we do about this? Well, let's start by figuring out how traffic even occurs. This was supposed to be a video, but it does not appear to be playing. So the idea behind, there's many sources of traffic. Obviously, if there's a car accident or if there's an intersection, there's sort of perturbations in the transportation network that causes traffic jams, causes congestion, and so on. But as we saw earlier, most of the driving happens on highways where, in an ideal case, there's not really much of this external interference going on. That still doesn't preclude traffic jams. So this was a study done in 2008 meant to simulate a highway traffic situation where you have a ring of cars driving around a road that sort of behaves like an infinitely long stretch of road if you sort of unloop the ring. And everyone was told, just drive at 30 miles an hour, or somewhere thereabouts, meters per second or something. So drive at a constant speed. And that was it. It's a uniform road. Everyone has the same instructions, same rules. And yet, spontaneous traffic jams just happen to form. If you can sort of see it showing up around here, where the cars are getting a bit closer together over here, spacing out a bit over here. Eventually, the cars would come to a dead stop at that clog, and eventually speed up again. You have a shock wave, a region of congestion that's moving backwards around the rim, or propagating upstream through a highway situation. Why does that happen? That happens because humans have a specific driving response. They're not bad drivers per se. Humans are safe drivers. If somebody in front of you stops, you want to be prepared to stop, so you hit your brakes. If they slow down, you want to make sure that whatever they're doing, you can account for. You may slow down a little bit sooner, a little bit harder. Eventually, these perturbations expand out to stop-and-go traffic lanes. And that's just the nature of human driving. Okay, so let's fix that by eliminating the driver. This was a very popular YouTube video, so we had over 9.5 million views. The simple solution to traffic: get rid of all the human drivers and automate it all. And there's a nice long video explaining how all of this can have benefits. If everything was an automated vehicle, we don't need to deal with this human response time. We can have a robotic response time that is faster, that is more prescient, and can eliminate these spontaneous traffic jams from forming. So yeah, a simple solution. Well, it requires automated vehicles. And we can see headlines like this that are now, as sort of more companies are trying more things, we see more and more of these. We don't have automated vehicles yet. We have some level of automation, adaptive cruise controls, and lane keeping. The technology exists, it's getting better, people are working on it. But we certainly don't have fully autonomous vehicles. That was the simple solution that was showed earlier. Now, I'm not bringing these up to as sort of pick on any companies or anything like that. I don't want to say that the technology is going nowhere. It's certainly improving, but there's still a long way to go. First, in terms of just the technical capabilities. That says nothing of policy about how these automated vehicles may integrate on the road. It says nothing about the innate desire for many people to actually drive their own cars. Ultimately, this sort of wraps itself all into a number of decades from now where we will still have some mix of fully human drivers and some amount of autonomy. Maybe full autonomy, maybe semi-autonomy, but there's a long period of time between now and when we can implement the simple solutions. And so that brings up the fundamental research question that I'm trying to answer. Is given the fact that there are some limitations on controllability and control penetration, what can we do? What effects can we have on the human drivers in the system, given our control efforts on some subset of the vehicles within that? So to frame that into more specific, particular questions that we're going to ask, if we have one vehicle that we have control over, what is the effect that it can have? And if we don't even have full control over that vehicle, can we still get that kind of effect? So that's what I'm going to be talking about today. So to start, let's talk about the humans in the situation. The goal is always to improve the lives of the humans in this situation. And so we can talk about a micro-simulation model of the human drivers within a traffic network. These are often referred to using car following models, where the idea is you're prescribing the behavior of a single individual vehicle or its driver in terms of its acceleration. How fast does it hit the gas or the brakes? Very, very pragmatic. This is the control that drivers have over their vehicles. And this acceleration, the rate of change of its velocity, is a function of what the driver is able to encounter. They can visually see the distance to the car in front of them. That's known as the headway. They can see how much that distance is changing, the headway velocity, the rate of change, time of change of the headway. And they can see their odometer, their speedometer, how fast are they going. So given just those three parameters, we can determine what's the right policy for acceleration or deceleration. There are a number of car following models that have been developed over the past decades. Some popular ones are the intelligent driver model or the optimal velocity model. I won't necessarily go into that in detail, just know that they're very complicated equations. They're nonlinear, they're high-dimensional, lots of parameters that describe sort of the state of the driver, the state of the traffic network, and so on. They've been they've been verified by actual data. A lot of data has been collected on drivers, and we can sort of map their models to this. And we can then evaluate what that behavior results in. In particular, we can look at what we call the uniform flow equilibrium. We can say, let's say we put a number of these vehicles, these drivers, on the road. One thing we can have is everyone sort of moving in lockstep. The same distance between each car, we call it the equilibrium headway. Everyone moving at the same velocity, at the same speed. We call that the characteristic velocity, the characteristic speed. If that's happening, then the headway isn't changing, so that the headway velocity is 0. The velocities aren't changing, so the velocity is 0. And we get this equation. This equation prescribes the uniform flow equilibrium. Everything is moving the same. And we can turn that into some macro scale characteristics of the transportation network itself. So we can take the headway, the equilibrium headway, and relate that to a density. If there has to be this much space between each car, how many cars fit on any kilometer of road? We can take that density and their velocity and relate that to the throughput, the flow rate of the network. How many cars are passing by at any given point every second? And we see a curve that looks like this. Now this has two regions that we can look at. Up here, this nice linear region at the beginning, that's called free flow. Every time we add another car to the road, we add that much flow going past a point. This is when there's no congestion. Every car is moving at the speed limit. This slope is the speed limit. But what we see as we add more cars to the road, as we increase the density, eventually we get a maximum flow rate, a maximum throughput of cars, and eventually it starts to scale down. Again, this is a property of human driving. If the headway starts going down, if you're much closer to the car in front of you than you would be otherwise, you necessarily slow down. You want a safe falling speed. And so as the headway decreases, as the density increases, the headway decreases, the equilibrium velocity, the characteristic velocity decreases as well, and we start to see these congested traffic networks, where the overall throughput is lower than it would be otherwise. So that's all well and good. That would be great if that's all the situation were. But it turns out we don't observe this in practice. So this is a bit of a complicated graph that I took from this paper here. But we can look at the graph that I had shown earlier. It's the green line up here, that's the free flow. And then this red dotted line was the congested fall. It turns out that's not stable. We don't ever see uniform flow in those densities. What happens is what we saw or what we would have seen on that ring road earlier, spontaneous stop and go traffic waves. And that's this green equilibrium line down below. What happens is any small perturbation in the uniform flow quickly amplifies and degenerates into stop and go traffic, causing a lower flow rate than we would have with uniform flow. We can see this from the math. So regardless of which car flowing model we use, we can linearize around the uniform flow equilibrium. So that's taking the gradients in each of the headway velocity parameters, turning it into a linear equation, and showing how the acceleration depends on those parameters with some linearization. Now, it's important to know these are linearized around an equilibrium point. So depending on which equilibrium point we are, what the density is, and therefore the headway and the characteristic velocity, we'll get a different set of coefficients. But regardless, we can treat this as a linear system, and we can get the transfer function. This transfer function gives us the offset from the free flow equilibrium for our vehicle as a function of the vehicle in front of us. Our driver's response is a function of what is happening in front of us. Okay? And so we get this linear system, and now we can analyze this linear system in terms of a concept called string stability. And that is fairly simple. If that transfer function ever has a magnitude greater than 1, then the system is string unstable. If it is always less than 1, it is string stable. The way to think about this is we may apply a perturbation to the car in front of us. Maybe it hits the brakes slightly to avoid something on the road, or maybe it hits the accelerator when the driver accidentally sneezes. Who knows? There's some perturbation. If the transfer function is greater than 1, then my response as a driver to that effect in front of me will be to have a larger perturbation. And as that propagates down the string of vehicles, it'll eventually grow so large that at some point somebody has to come to a complete stop. That's string instability. If there is no perturbation for which magnitude is greater than 1, then every perturbation will attenuate. It'll get a bit slower and eventually die out. So one thing we can say, if we have a number of vehicles on this string, all identical, then we just sort of multiply the transfer functions as a property of linear systems. And by this definition, since we're caring about the magnitude, if the individual transfer function is less than 1, the product of n of them is going to be less than 1. And if the individual one is greater than 1, the product of n of them will be greater than 1. So we can consider some unit cell. If they're all identical, the unit cell will be a single car. If it's a heterogeneous string, we can pick some repeating cell and evaluate that. And now this gives us the framework to analyze autonomous control. And so just like we had our linearized system for the human driver, we can build a linearized system for an autonomous vehicle, a controlled driver. This time though, the coefficients, the linearized coefficients, are not derived from some driver model, some car following model, but they're prescribed. We can go ahead and specify what our controller does. This is controller design. Okay? And based on that, we can get the feedback response of an individual controlled vehicle. And if, let's say, we put one controlled vehicle in a string of n human-driven vehicles, we can get the transfer function of that unit cell. Right? Simply n human vehicles, one controlled vehicle. And now we can evaluate the performance of this, again, in the same mathematical framework that we discussed earlier. So we can talk about the string stability. And we can say that this is stable if that transfer function of the unit cell is less than 1 over all perturbations. We can take this evaluation and flip it around. We can make it a constraint. Let's say that we require that our controller results in a stable transportation network. Well, if for that to be stable, if we specify that this is always less than 1, we can get a constraint on the number of human vehicles that we can include in our unit cell. That is, the number of human-driven cars that our controller can stabilize. We can say that it's as long as the number of human cars is less than this bound, then the magnitude of the transfer function is always going to be less than 1. So that's good. Now we've stabilized our uniform flow equilibrium. But we can do more. We can talk about additional parameters of the system. We can talk about safety and efficiency. They're two fundamentally different concepts, but they resolve themselves in math very similarly. We can talk about the headway of the autonomous vehicle. Now, if the headway gets too small, the car gets too close to the car in front of it, that's a safety concern. We want to make sure that the headway stays above some bound. However, if the distance gets too far, if the cars are too far spaced apart, that's inefficient. We're not making the most use of our transportation network. So we want to make sure that the headway stays below some bound. And we can bound this by some fraction or some multiple of the expected perturbations. So here we'll talk about delta as the expected perturbations that drivers regularly encounter on a highway. And once again, we can translate this performance metric into a constraint by requiring that inequality hold. And now we can get the number of human-driven cars that our controller can safely and efficiently stabilize. In particular, if we combine both of those, we can get our final optimization problem. What is the maximum n? What is the maximum number of human-driven cars that make sure both of those inequalities are satisfied? And we're allowed to vary our controller, the linearized parameters of our controller. We can play with that until we get the most efficient system. And so this is sort of the result. Again, we see our fundamental diagram. It goes up, it comes back down. We know that in this downward slope, inherently it is, if they're all humans, they're string unstable. But if we optimize in that range, we can develop a controller somewhere around here. Oftentimes, this is sort of like the bulk of the traffic. Again, transportation designers are pretty intelligent people. They want to maximize the efficiency of the network. They try to live up in that corner. Out there, we need about 3% penetration. That is, n equals 30. About 30 human-driven cars can be stabilized by this optimal controller that safely and efficiently stabilized by this controller. And in fact, if we go all the way down here into the super congested worst-case situation, we only need about 6% penetration. So this shows us that using this linearized analysis, we can actually stabilize at all these highway transportation networks using a small amount of control effort. We don't need every car on the road to be an autonomous vehicle. We need at most 6%. This now, as I mentioned, the human driver model is what we use to build this, right? The human transfer function is what we use in the optimization function to determine the optimal autonomous controller. But it turns out it's not that the optimal controller is not that sensitive to the human driving parameters. It degrades gracefully. So if maybe it's it's a rainy day and people are kind of grumpy and driving a little bit more aggressively, maybe we won't need 3%, but we need 4 or 5%. As the parameters change, we see a slow degradation, a graceful degradation in the behavior of our autonomous vehicles. And so that's great, right? We can take our traffic jam that's forming on these networks and throw our autonomous vehicles into the mix and eliminate traffic jams altogether. Well, it's possible. It's theoretically possible. We just proved that it can happen. But there's some important caveats, some important assumptions that we made to get that result that we can now start peeling away at to actually make this something that we can achieve. First of all, we did this on a single lane highway, right? There's just a single string of cars. Now, there's been some follow-on work on how to consider multi-lane effects, lane changes, and overtaking maneuvers. There's some more work that we can do on that. But even if we sort of ignore that, consider maybe a multi-lane highway as just a number of parallel single-lane tracks, we still have the issue that what we discussed here it was always the linearization about a uniform flow equilibrium. We need to still first get to that point. If we are in a uniform flow, this particular controller prescribes that we won't leave that flow. We won't fall into the stop and go traffic situation. But if we are already in the stop and go traffic situation, that's in the nonlinear regime. How do we get to the equilibrium, the uniform flow equilibrium? We need a full-on nonlinear controller to get there. Now, the other thing I mentioned when I was talking about the linearization, it's about the equilibrium point. That is, we need to know what the equilibrium state is, the equilibrium headway and the characteristic velocity. As of right now, with the analysis that we did, that equilibrium is prescribed by a We just assume that we know what it is. So again, if we want this to actually be out there in the real world, we'll need to figure out what that state is, and I'll be talking about that more later in this talk. We also need to find some nonlinear way of addressing the edge cases where it's not the uniform flow. I mentioned that we're considering this in terms of unit cells and human-driven cars in one autonomous vehicle. Well, for that to work, we need these cars to be uniformly distributed throughout the network. We know that the human-driven cars amplify perturbations, and so if we said, let's say n was 15, then after 15 human-driven cars we put an autonomous vehicle, it'll go away. But what if in the first set of 16 cars the autonomous vehicle was at the front, and in the next set of 15 the autonomous vehicle was at the back? Now we have a string of 30 cars in between. We've gotten our stop-and-go traffic situation already there. And so what we need then is to maybe perhaps have a higher density than was prescribed, just so that we can address the case when they're sort of randomly scattered throughout the transportation network. And finally, despite all of that, this assumes that we have full control of the vehicle. Once again, this goes back to the issue that we were saying earlier. We don't really have full autonomous vehicles yet. We can't implement this controller on a vehicle yet. And so, what can we do? And that brings up the next topic of this research. Let's keep the humans in there. Let's make this a human-in-the-loop controller. Now, the humans can then be responsible for that nonlinear behavior, like how to get away from the stop-and-go traffic into something a bit more reasonable. When we have human drivers, there's a lot more human drivers on the road. If we can get them to do what we want, maybe we can have a higher density, so we can address this issue of uniform density. And of course, now we don't need the fully autonomous vehicles anymore. So the idea is to use semi-autonomy. The idea to have perhaps a smartphone app. Everyone's looking at their phones anyway to do routing and navigation. Now, not only will it tell you, take this exit, make the next left, but it'll tell you how to drive. Drive at this speed. Maybe once we get the multi-lane questions answered, we can tell you which lane to drive in. It'll give you low-level microscopic commands for the human driver to implement. And of course, now this gives us a lot of benefits. For one, we have all of this technology available right now. People are driving with cell phones mounted to their dashes, giving them instructions. We don't need any additional technology development on autonomous vehicles. We don't need any infrastructure built into the highways. We can just go ahead and do this. And in fact, we can do this very well. Many cars on the highway have cell phones giving them instructions. If we get some fraction of that, we have densities that are much higher than the 3 or 6% the minimum that we needed. But there are now some challenges to address. In particular, we've now put a human in a control room. We need to model how a human responds to commands. There's compliance issues, there's delays and speed of response. And of course, the thing that we mentioned earlier, this is all still done in analysis around the equilibrium point. We need to figure out what that equilibrium point is and use this system to determine that network state. And so for that, we've developed this human-in-the-loop test bed. How do we figure out how humans respond other than by observing them? So let's build a remote-controlled car and drive it around. It's a lot easier to do tests of this than on some full-scale car driving in actual traffic. And so we built this vehicle. It's a 1/28 scale, so it's small and compact, can sort of drive around in your lab. It has realistic handling of the vehicle dynamics. So the rack and pinion steering is just like in a car. It has grippy tires, just like a normal car would be. It allows for visual feedback. We have there's a wide-angle camera in the front that captures sort of back to about here, just like you would see in a regular car. You have the vision in front, the sides. We can then pipe that through to a driver station. So there's the camera taking the video, you show it in your video screen, you have a steering wheel and pedals. You can pretend like you're driving an actual car. And the way we have this configured, there's a controller that lives in the middle of the sensors, the camera and the visual feedback, and the controllers, so the motors and the servos that drive us. So we can have several of these vehicles behave autonomously, we can prescribe the control, and the rest operate under human controls that we can then interpret what is happening on the driver's side. Another nice thing about this is low cost. Now, not as low cost as some of my other work, but this is about between $100 and $200, which for realistic driving simulations is fairly good. We can take that hardware and put it into a simulator. So now we can talk about simulation based on just the prototype system. We can also simulate this in a virtual reality or augmented reality world. We built a simulator in Unity that matches up with the physical test bed. We put this all in a motion capture system, so we have ground truth. And now we have autonomous vehicles driving around here, human-driven vehicles driving around here, and we can try some scenarios. If some of them are unsafe, even for the prototype test bed, we can just instead do it in virtual reality. And so now we can sort of insert ourselves into the loop and figure out what is it that a human driver is doing. We can put several of these cars on the roads and start investigating multi-lane maneuvers. So one of the first things we looked at was overtaking. So it's still somewhat of a linear system, but with this one nonlinear jump in between there. But now we can also talk about lane change maneuvers and how to handle multi-lane traffic. But the key point about this is that it uses computer vision. So it has a camera on there, off-the-shelf camera hardware, off-the-shelf processing hardware, and in fact even off-the-shelf processing algorithms that we stitch together with our own custom glue that lets us parse the visual scene. And we can do some segmentation, decide what's a road, what's a car, and do some state estimation on that. Figure out how far the car is in front of us, how far it's moving, and of course we already know how fast we're moving. We have all of the inputs into our autonomous controller. We throw all that in, and we can say, look, here's how our autonomous vehicle should drive. And so this gives us the ability to now implement our controller, our autonomous controller, in the real world. We translate this from our prototype system onto a cell phone, mount it up on the dash, have the camera look at the scene in front of it, and there we go, we have our semi-autonomy. Now, this visual perception, it gives the state information that we need to determine our acceleration profile, but it doesn't give us the equilibrium state information. It doesn't tell us what the characteristic velocity is. And so this is an experiment that was done by folks at the University of Illinois, which is sort of recreating the system that we had talked about. A single autonomous vehicle in a string of human-driven vehicles. Now, again, they did, instead of having an infinitely long highway, which I don't think Illinois has the money for, they connected the end at the beginning and made a ring road. And what they did, again, was try to drive this autonomous vehicle about an equilibrium point. But the equilibrium point was prescribed by an oracle. And so the actual characteristic velocity was about 7.5 meters per second. And you can see, without the autonomous vehicle, you see stop and go traffic. If you have the autonomous vehicle controller prescribed at 6.5 meters per second, the stop and go traffic waves go away, and the cars are all driving around 6 meters per second. 6.5. 7.5, same thing. No traffic waves, and the cars are going at the prescribed speed. But if you misjudge your equilibrium velocity, your characteristic velocity, the stop and go traffic waves return. So this sort of highlights how important it is to have that state information, not just the local state of your headway and velocity, but the global state, the network state. What is the actual characteristic velocity that you should be striving to achieve with your autonomous controller? And we can sort of do some more analysis of the effect of a mismatch between actual characteristic velocity and command velocity. You can sort of see here, if you're going too slow, if you're prescribing a speed that's less than the characteristic velocity, you're not using the system as efficiently as possible. penalize that. Let's try to make sure that we have maximum efficiency of our system. If you try to go too fast, then you hit the stop and go traffic waves. And once again, you're incurring a cost. And so you can sort of see here, this heat map, if you have a specific characteristic velocity, the true equilibrium, and you command some other velocity, you really only reap the benefits when the two are very close to each other. So one thing to note, by the way, as an aside, you see this graph, this dotted line is what the actual characteristic velocity is, assuming the car following model at uniform flow equilibrium. As the command velocity increases just slightly beyond the characteristic velocity, we still see some increase in performance. That's because we had replaced one of the human-driven cars with an autonomous vehicle. That autonomous vehicle is a better driver than the human drivers. It doesn't need as much headway to be safe. And so the effective density of the network has dropped. So that's another point that we can maybe play with as we go forward and look at more sophisticated controls. But regardless, we need to estimate the characteristic velocity of the network efficiently. And of course, if we're using just our local measurements, just being able to see the car in front of us, it's really hard to extract that information. So there's a number of trials of a constant characteristic velocity, but a vehicle going through many different traffic jams. You can see the duration of the traffic jam is different. The duration of the non-traffic free flow period is different. It's very hard to extract meaning from this alone. And so we turn to some notion of distributed algorithms. And this is where I'll take a step back, and I'll frame this in terms of the traffic question that we've been working on. But it's really a much more general question. The question of how do we make use of distributed sense information about a state variable in an efficient and algorithmically rigorous way. So we may have a bunch of nodes that are spatially separated. They can each sense various aspects of a state to be measured, and they can communicate that information to each other. So typically the way this kind of distributed sensing is done is there's these two black boxes, sensing and communication. The sensor runs on its own speed. The communication runs on its own speed. Every time there's something in the sensor box, we put it in the communications box. And it requires this sort of network-wide connectivity. Anytime somebody takes any sensor measurement, that information gets passed to everybody. Everybody has the same information. They have the most information. We get a good estimation. But it turns out the world is not quite like that. We may have some cars that are enabled with our hardware that are able to take sensor measurements. So the green lines are the sensor measurements. People are able to observe other cars. But not everyone can observe the same set of cars. And you may not be able to communicate with the car that you observe. You may be able to communicate with a car that you cannot observe, but both of you can observe the same car. These sort of connections, this topology that shows up, is very difficult to address using the conventional distributed state estimation algorithms. And so often, if you have unreliable communication or perhaps sparse communication, data is just dropped. Or you may just need to resend it multiple times in order for the data consistency to still be there. If you don't keep track of who's sending what data and whether it's repeated data or not, you may end up with a mismatch between your sense of the uncertainty of the state and the true uncertainty of the state. Getting two identical sensor measurements doesn't actually give you any more information if it's the same sensor measurement, but two identical numbers from different sensors gives you far more information. Maintaining consistency of the state estimate with its uncertainty is difficult to do when there's disjoint topologies between observation and communication. And so our goal is to put all that together in a new algorithm, a new distributed state estimation algorithm, where we consider every independent operation that's possible by these nodes. We can take so we can sort of evolve our state estimate, our understanding of the state, using dynamics. We say, all right, we know how fast we're going, we know how fast other cars are approximately going, this is where they were before, next time this is where they're going to be. That's time propagation. We may take a sensor measurement, and we say, all right, I see this other vehicle, I take a GPS reading, I look at my odometer, my speedometer. We can take some observation and derive some information about a state, whether it's our local state, the environmental state, or some combination of the two. Finally, we can do some communication. I can send some information to another node in the network. Someone else can send their information back to me. Each one of these actions that we can do has some effect on the local state and the global state, as well as its uncertainty. How much do we trust what we're seeing? And that's represented by the covariance in a stochastic state estimate. And so now, with this framework, we can develop the algorithm. We can figure out the math that takes these various topologies, takes these sort of various scheduled and activity plans for which operation to do at what time, and turns that into some knowledge about the system. And so for that, we created a covariance intersection Kalman filter. And so we can see in a time update, as we sort of propagate, the state just evolves according to the dynamics that we have assumed. And the covariance grows according to some uncertainty that we have introduced by not knowing what the true state evolution dynamics are. Every time we take an observation, we adjust our state estimate based on what we saw. We adjust our uncertainty, again, based on the information that we received. And similarly with communications, when we hear about information from some other node, we adjust our state and our uncertainty accordingly. And we can come up with procedures for doing all of these in such a way that each node within the system, each agent within the system, maintains a set of information about the state across the entire network and the uncertainty associated with it. And so we can build in a Riccati recursion that tells us how does that uncertainty and the state evolve over time. We can use that if, despite having disjoint topologies. So when various things can communicate or observe, we can make sure to include all that information into this global Riccati recursion. If things happen at different rates, if every operation is a discrete time operation, we take a sensor measurement right now, we communicate right now, but maybe we wanted to do things at different rates. We want to talk a lot faster than we sense, or sense a lot faster than we talk. We can put that all into a continuous time Riccati recursion that bounds this, and now we can actually do mathematical analysis on this and describe exactly how good the state estimator can be. And well, it can be pretty good. So the pink line down there, that's the benchmark. That's what happens when all information throughout the network is exchanged to all nodes, and everybody computes sort of the best case state estimate across the system. With ours, we don't assume that we have dense dense communication. In fact, we only allow 10% of the capacity of communication throughout the network, and yet we're still able to maintain the same. These are plots of the actual error of the state and the uncertainty within the state, within our local state. We can never observe the actual error. We need some ground truth for that. We can sort of do it in a test bed, but we don't know it in real life. This uncertainty, the trace of the covariance, gives us our representative measure of how much do we think that error could be. And we can see that for both of these, we match the performance of the centralized equivalent Kalman filter, and we maintain consistency as well. The actual error is within the bounds prescribed by the covariance estimate. Oh. And so that means that with this sporadic communication, we don't need all of the cars in our network to have the same app running. We don't need to be able to talk to all the cars in our network. We only need to be able to talk to a subset of them, and whoever we can talk to, we will make use of. And if we can observe more, that's even better. And moving forward with this, we can turn this into some optimization problems. Each operation that we take consumes some amount of resources. Maybe it consumes some amount of power to run a sensor or to communicate. Maybe it consumes some amount of bandwidth that is limited in some B2B network, vehicle network. Maybe there's an actual cost associated with communication, such as if we're using like a GSM or cell phone network. So we can talk about minimizing the cost. We saw earlier in the heat map that we're allowed some amount of uncertainty between the actual prescribed, or the actual characteristic velocity and the prescribed command velocity. If we say we have some amount of error that we're willing to tolerate, we can formulate an optimization problem. What is the cheapest way to do it? What is the most cost-effective way to do it? Or we can flip it around and say, if we have this budget, this resource budget, what is the best state estimate we can get? And so we can, again, run this on a real-world simulation with some parameters for sensing and communication costs. And we can see that with these optimization problems, we can minimize, we can try to minimize the resource consumption, keeping our error within bounds, and we can see that our, that's the second line, we save almost 60 to 70% of the resource communications while still maintaining the same error bounds. Or we can flip it around, try to stay within the power budget, but minimize the uncertainty. Turns out we can do both. We can minimize the uncertainty at the same time as we reduce the communications, or the total resource cost. And so ultimately, this framework for distributed state estimation is much more general than traffic, and we can see that we can make use of a lot more information than we have been using currently. And we can keep going forward with that. As we look into these mobile networks, we're driving around. Things are changing. We can see some things now and not see them later. We can communicate with some things now and not later. Maybe a truck passes between or something like that. How do these dynamic topologies impact the state estimation? And in fact, we can maybe make use of these dynamics to say, well, if we know things are going to change, maybe we can delay some of our operations to make the most use of it. One additional sort of area of interest that we're working on is, right now, all the representations of state are the obvious ones. If we're talking about position, it'll be x, y, z position. If we're talking about velocity, it'll be meters per second. Maybe that's not the best representation of state. Maybe instead of headway and characteristic velocity, the actual representation of state is some other function of those that may not have Gaussian distributions. Common filtering is very good for normal distributions, but if we have a specifically known distribution that's not Gaussian, maybe we can come up with a common filter like state estimator that makes more effective use of this knowledge. So we've been doing some work on that, especially related to like machine learning or neural network brain learning type representations of state to come up with some more optimal ways of defining this. But regardless, I'm running close on time, so I'll wrap it all up by saying what we can do is we can put together all of these things that we know. We can co-design across these various engineering boundaries. We can do the linearized model analysis by trying to find out what happens to vehicles, cars, and humans and autonomous vehicles around the equilibrium position. We can make sure that we include the humans into consideration, whether they're the passive drivers around us or an active commanded driver. We can sort of wrap this all up in a principled mathematic framework that lets us go through and say, you know what, we have the hardware technology to be able to ameliorate this traffic congestion, to lower the costs associated with traffic jams and so on. And so with that, I'll say go Bears, and I'll take any questions on any of the stuff I've talked about today.
Did your team attack this acceleration, deceleration, perturbation issue because it was determined as a primary human cause of these sorts of traffic clogs? Is that what you determined some other way? I didn't remember seeing that slide.
Right. So the human causes are that humans are safe drivers. There is a response to the car in front of them, and it just turns out that that response necessarily is unstable in certain congestion regimes. And so what we're not trying to change the behavior of the humans that are on the road. They're going to drive the way they drive. And honestly, we probably want them to drive the way they drive, just so to make sure that things stay safe. But what we can do is say, knowing that they drive how they drive, we can influence the overall behavior by giving them a cause to respond to. Driving in a way that makes that we know how they're going to respond, and hopefully keeps the entire network moving smoother. Did that answer your question?
There's other causes, like you got really aggressive drivers and really passive drivers, and the mixture of those creates its own problem, even beyond this. And I'm just wondering, of all the social situations you looked at, this was the number one, this acceleration, deceleration one. Is that kind of the main cause?
I see. So you're absolutely right. There are many different causes of congestion and of traffic jams. Now, we haven't done the analysis on which is the most significant cause. You know, there may be any of these, but you know, the metrics earlier showed that 75% of driving happens on the highways. And you know, on the highways, there's very little other cause. There's sort of very little externally imposed effects that cause these perturbations. And so we have an assumption that this is one of the strong causes of traffic jams on highways.
just taking that one little step further, to what extent in national practice and national effect is that 75% drop down by the effect of interchanges and the finite, the very finite length of some of these stretches over which the analysis and the behavior could be expected.
Right. So I'm not. I don't have the data available for that. A lot of people have done that kind of analysis, and so I'm sure other people in ITS will be able to sort of call that up on a moment's notice. There's actually a research program going on right now at ITS trying to evaluate a little bit more information about that question. So looking at a major arterial, a major highway with all the arterials around it and the interchange and so on, how does all of that affect everything else? It's a very high dimensional system, a lot of sort of parameters that go into that. It's perhaps somewhat difficult to estimate, but I think it's certainly worth knowing and evaluating going forward beyond what we've done here.
So you'd hope for some extensions of this to more elaborate topology.
Of course, right? This is just the beginning, right? We're just looking at one cause of traffic, one possible solution to it. As we start building out the mathematical frameworks explaining this, hopefully we can expand it more and more to be able to address more sources of transportation inefficiencies using just some low fidelity, low penetration control.
What would be the motivation for a person to get autonomous vehicle that improves the systematic efficiency rather than her or his own gain?
That's a great question. So this, as we presented in here, the autonomous vehicle is controlled, optimizing for the system efficiency. And so where is this incentive? Why should somebody voluntarily benefit the overall network? Well, I think I have a sneaking suspicion that most of us are intrinsically good. And maybe, we woke up early one day and we say, I'm willing to spend an extra minute on my commute to make sure the 100 people around me spend one fewer minutes on their commute. And this has sort of been backed up by practical implementation. There's a driving app called Waze. Some of you may have used it, where the users are responsible for contributing information. There's a slowdown here, a broken down car, a pothole. It takes effort for a user to go through and input that information into the system, and people do it. People did it in droves. I mean, sure, okay, they got some reward. The more you contributed, the shinier hat you got on your avatar. Maybe we can use some of that to incentivize people to participate. But really, people like being a conscientious citizen. Maybe there's a way of spending a little bit more of your effort and time to make the world a better place. Now, one thing that we can go a little bit forward as we sort of build out this mathematical framework is maybe we can include a knob. Today, I'm running late. I can't afford to be any later. Let me put my control knob all the way over to maximizing self-interest. Tomorrow, yeah, I woke up in time this time, and I'll put it over to being a conscientious eco driver. These are things we can play with as we sort of build out this framework.
I guess my detailed question is, if we actually take that autonomous vehicle, for example, like the acceleration profile, is that too uncomfortable? Could it be uncomfortable for the rider?
That's also a great question. Yeah. So I pointed out in the slides, but we included limits on the maximum allowable acceleration of these autonomous vehicles. The assumption is that there's a human inside. There's comfort bounds as well. We include those in the optimization procedure to generate the controller to ensure that if there is a passenger, they are comfortable. Now, one interesting thing to think about may be if we can improve the traffic flow significantly enough, maybe we don't need human-driven, and assuming we have the autonomous technology, maybe we don't need human-driven cars to be the pace keepers. Maybe a municipality, the city of San Francisco, can have a fleet of 1,000 cars, and they'll insert them into the roadways in such a way to maintain the efficiency of the entire network. So it's another thing that we can think about.
I'm so sorry to interrupt the discussion, but it's Friday night, so I have to interrupt. Okay, so on behalf of ITS, so here is the small cake.
Thank you.
Thank you for your presentation, and please join me in